let's say a few words about the speed of light as an absolute speed limit using our light clock as an example. Remember, we derived our expression for the Lorentz factor gamma in this form, 1 over the square root of 1 minus v squared over c squared. Clearly, there is a problem here if, remember, v is the relative velocity between two reference frames, two inertial reference frames. We've been using Alice and Bob. So if Alice is stationary, she sees Bob perhaps go by in a spaceship at velocity v, according to her lattice of clocks and measurements. And then Bob could be, in his spaceship, could imagine, really, he could be stationary. He could see Alice receding behind him at negative velocity v, according to his lattice of clocks and measuring system. So v is the relative velocity between the two reference frames, c the speed of light, of course. If the relative velocity between two reference frames is c, if Bob is traveling by at the speed of light compared to Alice, and Alice measures Bob at the speed of light, look what happens, of course. We've got c squared on the top, c squared on the bottom. This is 1. 1 minus 1 is 0. Square root of 0 is 0. 1 divided by 0 is infinity. Gamma becomes infinite. So that's a hint right there, a very strong hint, that something either can't go at the speed of light, or we have problems with our theory. And since the theory has been well verified, we say, okay, this must be an absolute speed limit, that nothing can actually get up to the speed of light. You can do further calculations with this that really go a little bit beyond our course in terms of the amount of energy needed to take a massive object, anything with mass, and get up the speed of light, and you find it essentially infinite energy is required. So there are other arguments too for why you can't get there. There are actually, over the last, it's about 30 years or so ago, there's the idea that maybe you can't get to the speed of light, but perhaps there could be things that actually were faster than the speed of light, sort of on the other side, as it were. And they were given the name tachyons. There was some theoretical work done on them, some development to figure out whether this would actually work out. The theory ran into some insurmountable problems along the way eventually, and therefore was discarded. But for our purposes, certainly, the gamma factor, the Lorentz factor, is indicating can't get up to c. You can get close to c, in which case gamma becomes very, very, very large, but you can never quite get to c because then it becomes infinite. Now, let's see how that factors in with our light clock example. Remember, from the light clock, we found that the elapsed time on a moving clock, if I'm observing here, we've got two identical clocks. Maybe Alice is here with me, and we see Bob going by with his light clock, and we compare the two. The light that we see in his clock has to travel a longer distance than the light in our clock, and therefore his clock ticks longer. I should really say ticks slower. Each tick takes a longer time to go from here in this diagonal path versus our just up and down path with our identical light clock. And therefore the elapsed time on a moving clock is less than the elapsed time on our identical stationary clock. So this is us observing Bob's clock going by. Remember, for Bob, his clock, he's just sitting there with his clock. It looks fine to him, and he's doing our clock as running more slowly than his. And again, it all goes back to the two basic principles that Einstein enunciated, and the fact that simultaneity and clock synchronization is relative. But just to remind ourselves, time dilation. Elapsed time on a moving clock is less than the elapsed time on an identical stationary clock. Here was the formula. So again, delta t, the elapsed time that we'd measure in the lab, is gamma times the elapsed time on the rocket clock. So the number of ticks on the rocket clock, maybe we get 10 ticks on the rocket clock as we see. The number of ticks on our clock, depending on gamma, might be 20 or so if gamma was 2 in that case. The moving clock would run more slowly. Or just to reverse the equation here, the rocket clock, the elapsed time on the rocket clock is going to be less than the elapsed time on the lab clock by the 1 over gamma factor. Well, what if gamma then is infinite? What if we put c in here and make gamma infinite? Look what that indicates with our time dilation equation. Well, first of all, we haven't encountered anything in physical reality that is an infinite quantity. And so that's why even the math might say it's infinite. We say, we can't have that physically. But just imagine if we could here, this would say that the elapsed time in the lab equals infinity compared to the rocket clock. That's sort of weird. That how do you have an infinite elapsed time on our lab clock ticking away right here? Get a little more insight perhaps with the second equation, that this says the elapsed time of the rocket clock, 1 over gamma times the lab clock. So whatever the lab clock is saying, 1 over infinity, if this really is infinity up here, that's just 0. It's saying no matter what the lab clock says here, the rocket clock is 0. In other words, the rocket clock never moves. As the lab clock is ticking away very nicely, we're looking at here, it's ticking away nicely. If Bob was moving by in his rocket with his light clock there, and he was moving actually at the speed of light, we would see his clock as never ticking at all. It'd just sit there. It'd be frozen. Time would be frozen as far as we would see his clock going by according to our lattice of clocks. In other words, we'd see him going by, and our lattice of clocks would be there. We could take flash photographs all the way along our lattice of clocks and look at those photographs later and see what Bob's clock said along the way in each of those cases. And his clock would be the same thing for all of them if he was traveling at sea. His clock would never tick at all, even though ours were all ticking nicely. And we can see that geometrically a little bit with our light clock diagram here. Remember, this is like 3 snapshots of the light clock. Snapshot 1, snapshot 2, snapshot 3. It's moving at velocity v here, and so we had the light beam as we see it in the lab. As Bob goes by, his light beam on his clock would go up and then back down again, bounce off the upper mirror here, and then down to the lower mirror. That'd be 1 tick, while our clock would just be going up and down like that. Well, think about what happens if v equals c. So if we say, just do this even in orange here. So we'll say v equals c. What happens in that case, sort of geometrically here? Well, that means from 1 to 2 here, okay, his light clock is moving with velocity c. In that amount of time, okay, to move, say, this distance here, green, so in that amount of time it's moved that distance there. So, to get to this position too. So if this light beam here is traveling up toward the upper mirror, how far has it moved? Well, it's moved the same distance. So if we sort of spin this up here like that, that's where that light beam would be at that instant. When the light clock gets to position 2, it's moving, we're assuming it's moving at velocity c, speed of light. It's moved to here. The light beam heading up to the upper mirror can only go that far. And so what happens then, when it gets up, presumably to that mirror's not there anymore. Because a little bit later on, it's moved now over here to this position here. So it's right there. And the light beam can't hit the mirror there. In fact, the light beam can never hit the upper mirror, because the upper mirror is always just out of its reach. And in another analysis we'll do later on, we can actually do this more quantitatively to show that in this instance, the light beam will never hit the upper mirror. It will never get there. This is another way of saying the rocket clock is frozen. The light beam actually, in fact, as you elongate this out, the higher the velocity here is, in terms of this triangle sort of gets elongated out this way. So a very high velocity, the light beam would go way over here and bounce, and then way back down. And when it gets up to C, it never can catch up to that upper mirror. And so it never ticks at all. And it actually becomes just a horizontal line there, never reaches the upper mirror. Rocket clock is frozen. Again, we'd say that's an unphysical situation for a moving object like our light clock here, and therefore we don't expect it to actually happen. But again, the math here gives us some hints that, that's a very strong hint, that that's not possible. And that's backed up just by looking at the situation physically or in a geometrical sense, that the light beam heading toward the upper mirror will never be able to reach it, because the mirror is always, because the mirror is moving at velocity c is supposedly this way, it'll always be just out of its reach. So interesting to see how the velocity of light then becomes an absolute speed limit. Later on, we'll also see that there's some cause and effect arguments that also say why this can't be possible.